Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have lecture 4, Parallel Programming with OpenMP. And this is not OpenMPI, so this is not about the message passing interface. Indeed, it's about a standard or de facto standard really for using shared memory with OpenMP. It's usually a problem sometimes that students get confused by OpenMPI and OpenMP. So these are different things. OpenMPI is an implementation of the standard of MPI, and OpenMP is a language we will learn today in order to do parallel programming with shared memory. Hence, we will also use this lecture a little bit to differentiate between distributed memory, what we know now very well with MPI, but also a little bit, what is the key in shared memory? What are the limits? What is a comparison with MPI? And so forth. OpenMP with shared memory leads also a little bit into the space of GPUs, so graphical processing units, or more accurately, general, processing GPUs, graphical processing units, GPGPUs. But, this is something which we just sketch a little bit today in order to have then lecture 5, where we then, of course, talk much more about accelerators and GPUs. So, however, before we go into the lecture 4 in detail, it's time to review a little bit our conceptual lecture 3, because we'll see some analogies, of course, today when we do shared memory, especially also facing limits, of course, because shared memory, as the name suggests, everybody has access to the shared address space. This is limited. So what can we do about it? It's about hybrid programming. We will learn this a little bit too. But the parallelization fundamentals that we learn in lecture 3 were also very relevant, essentially, for basically what we learned today. So the last lecture was really thinking more conceptually, what is parallel computing? Why is there a speed up? What does the speed up bring? And we started a little bit with an idea, very simple. We have an array of 16 elements. You see that here on the top left, which we would call now, in one respect, our domain, right? Hence the name of domain decomposition. So admittedly, this is a very simple domain. We come to later ones. You remember these ones are then more heavy weighted domains where we have to think about domain decomposition much more. But when you think now the simple array, we learned several things with it. The first is, in a way, if you have 4 cores available, for instance, right, we have multi-core these days. That means we can also use shared memory, maybe here, basically 16 elements of an array would be not a big problem. So the conceptual idea of parallelization stands. I can break this into 4 parts, right, in order to figure out the local maximum in these 4 parts, which you see there depicted a little bit. But it gave us also the opportunity to learn about some aspects, and this is the master worker paradigm, and also some sort of load imbalance that we had the last time. So this is really important terminology, what we learned, because you learned that this is a graphic which is sort of not really true, because if you have even 4 cores to break down the local maximum of all of these array, which might be useless actually to do in parallel computing, it's just more an image for you. Still, we see that there must be someone also computing the max global out of these 4 maximums, right? So this is a graphic which is sort of showing not the reality. That means even if you do this, let's say parallel, that's fine. You have still some of these cores having the responsibility to do the maximum of all these local ones. So gather firstly all the results, make the computing to do the global results, and then report it or write it in a file. And this would mean that core 1 necessarily takes longer than core 2, 3, and 4, right? And this is the sort of thing that that life, and when we now talk about real domains, real decomposition of larger domains, it is not at all that simple to say, well, let's break down a big problem into 4 single pieces. Everything is nice. Everything is actually quite homogeneous. You will find also here on the ocean, right? Depending on if we do ocean wave simulations, then we see that these parts that having these processors assigned, and we learned that a little bit last time with these domain decomposition here, because the overall domain might be not mapped per grid per one processor. You can have here also 8 processors tackling one part of the domain. But essentially, you mean when we do wave propagation on the ocean, you see that these parts would be necessarily having much more to do, communicate than maybe those that have lots of land in it, because on land we don't do waves. In other words, much less load. So, and this would lead to lots of load imbalance, right? When we have this kind of domain, done. Of course, luckily, people would be also maybe in this context also want to compute the atmosphere, which is also above those tiles. So there would be still something to compute. But the load to keep them balanced, like the, let's say, the kind of image that you see here really is not at all that simple. And that was really one of the takeaway message last time from parallelization. Parallel computing is not that simple. Just throw more cores to it and it will be faster. Right? There are many showstoppers. There are many ideas where it looks quite brilliant to chop down a big domain in smaller pieces. And this is not at all a kind of balanced load, hence load imbalance. In other words, some of the CPUs we have, or the cores, or GPUs even, they will be idle, right? Because they're waiting for others. And that's what we also learned last time, which is a no-no in HPC. We want to use essentially the HPC systems to the maximum degree, and idle resources is never good. Hence, you should come up with a much more adaptive domain decomposition, advanced material that we don't cover here. I gave some example of advanced material, which is, for instance, the adaptive mesh refinement that is often used in, let's say, computing, where the mesh or the domain decomposition, if you will, is moving along a little bit with the computational requirement, with the needs. So adaptive means there that the grid, or basically the mesh, is always refining itself depending on the computational complexity. But yeah, please go ahead and look again in lecture 3 if some of these terms are not still clear to you. Another element which is very relevant for MPI, and then also in some respect when we talk about hybrid computing today and hybrid programming with OpenMP and MPI, we have this halo and ghost layers, another sort of idea where we learned a couple of things with, which are important to repeat. So the first is that when we do simulations, right, the wave propagations over the ocean, the atmosphere simulation of the next, let's say, 10 decades, how will the Earth will be? This is all dependent on so-called time steps. Usually the physical formulas we compute have a sort of idea of, we have a certain time step, and then for the next time step, we compute again the physical formulas. But of course, we have to see how our neighboring, how our surrounding has evolved as well over time, hence the other processes. So you could see that a little bit with here, this time dimension that I modeled here with T0 and Tier 1. So this is about the time steps as an example, and you would say that T0 will be computed, and the T1, the next time step, is heavily depending on the inputs from the previous time steps of the neighbors, right? In other words, we need to take our neighboring into account. Now, the other thing to take away is that, of course, when we do now today shared memory in this lecture 4 here, we will see this space sort of, which is here out of the book. The shared memory will be also a little bit limited, right? We cannot put everything into the memory of one processor if you want to have this large scale simulations. Maybe it works for the coarse grained scenario, depending on what I want to do. Maybe today memory is quite big these days. We can still solve it with shared memory, but if you go to higher scales and involve maybe not only wave propagation, but atmosphere, land surface interactions, and lots of other physical formulas, chances are that the computational capacity would be, of course, too little, but also the whole amount of memory, the information of the whole, let's say, propagation of the system, the old properties of the system, all of that would be not enough in memory. Hence, we have to talk about distributed memory. And then by using this concept, we learned something which we would say we're leaving the end of one domain into the other, right? Let's say between these blocks. Now, the trouble we are in is then that we are dependent in the next time step on the time step before. But how I should do this when basically the time step before was actually computed on another processor. So this is something which is sort of a common paradigm, leads also into stencil methods and so on. But there, the halo and ghost layers, coming back now to this terminology, have been introduced as a way forward, where you will find many codes where they do lots of physics, lots of interactions, but before they go to the next time step, similar like you see here depicted, they will fill the ghost layers of this one domain with the data on the corner of the other domain and vice versa. You see this quite nicely on the image, showing you also that essentially what you see here, and this is now referring to the term ghost, this is actually in the real world not existing, right? That's very clear. It's just a fake, just to store variables that can be then used in computing the next time step. And every time you see here, these two take away the message that this is the same paradigm applied to every part of this grid in domain and domain 2. So I think that's sort of very obvious. And again, coming back to the load imbalance kind of code that we have learned is more from the, let's say, data mining, machine learning area. Here we have the HPDB scan in parallel code. And you see that when we want to cluster these points, which was one of the tasks here, you see quite a load imbalance when we would have a typical grid over it. Hence, the domain decomposition might be still inspired by a grid, of course, because it has certain properties, but the real, let's say, processor decomposition might be still assigned differently, right? You see processor 1 has just this fraction here, while processor 2 has quite a big grid domain, but the point is that the most of the computing will happen here. Why? To cluster it into one cluster. It's very obvious that these are outliers, or maybe they form a cluster and these are outliers. They're far away. There's not much to compute about, basically Euclidean distances and so on. Hence, in other words, load imbalance can be very quick, not only in simulation sciences, but also we see here in a data mining application as well. And then we went on and said, okay, speed up is something we're interested. So more cores should mean, fast execution. And when you see that here, we saw essentially two laws where we have essentially putting more and more cores to it, and a certain tail off means we have this kind of strong scaling idea, right? And here the idea is, if you remember a little bit, like keep the work constant, right? Of course, you have here different ends, which you have in order to, show then these different, let's say, types of what you do. But in each of the different adding to the number of cores, you keep the work constant. Now, that is very different from weak scaling. And again, we see here the quite difference. We changed the particles per core. We didn't change them here. They remain the same, right? In strong scaling plots. In weak scaling plots, we see that basically we give them more work, right? The cores, basically in terms of getting more cores, the simulation gets also bigger because we keep the particles per core more and more constant. And with this, we are filling, let's say, huge machines. You see here 460,000 cores, even on an older HPC system, but it doesn't matter. But the same problem applies that, you cannot just always increase the number of cores and it will be just growing and growing in terms of, the efficiency that we then see. There will be communication overheads more and more when you use really 500,000 cores approximately here. So there will be several different showstoppers that gets away from the ideal performance. And this is another part which is really, let's say, showing a bit the trouble of speed up. You cannot just throw more and more cores and it will be always better. And there will be load imbalancing as well. Or let's say the efficiency goes down. In other words, the CPUs or the GPUs even don't have enough work to do, and parts of it is again idle or so. So this is something, they wait for communication, for instance, instead of compute. So these were important terms, but you have lecture 3 to look at this. So let's go ahead with lecture 4, which is now parallel programming with OpenMP, another practical topic because some things you will do in your assignment. And this really starts with shared memory programming concepts. We will learn OpenMP has several concepts called regions. What is a parallel and serial regions? We will start with, and then quickly how we talk about threads instead of processors. Hence, we will fork different threads to do different work. And this is sort of, let's say, some say in my course, easier than you do an MPI, because you sort of do a, let's say, not really programming of this, but you change source code to be in parallel. And I will make the point of it when we talk about Sentinel and so on and so on. But before we go into the details of programming, really, I want to also show some benefits of using OpenMP, because in some respect, shared memory can be even done with normal Unix code, C code. So there's the question why OpenMP exists and the standard, which enables us then, of course, better portability. And then there's also this motivation where I said we can always, combine shared memory with distributed memory. We'll have a look at this where we talk about hybrid programming motivation. And then, of course, these days we do lots of Python. So we also will look at some Python ideas to do it, coming to PyComs and COMS, which then leads actually to a bigger picture that when you talk about already these tasks that we give different threads, you easily can come to the idea of a rather big workflow, a task-based executions and following the data flow instead of just think about always computing. And this is something what we will also show you with OMS and so on. And the second part will be then really looking a bit more to the practicalities of using OpenMP with our Hello Threads program, of course. First, basic building blocks of Sentinel, how you use shared memory, what's the difference between local and shared variable types, and how you can quickly parallelize loops, for instance. By doing, let's say, source code that is influencing the shared memory address space, it is also important to recognize that we have some regions where this is maybe a little bit critical, or you need synchronization on it, because several different threads want to access maybe one variable at the same time, not for reading, but maybe for reading and writing at the same time. So lost updates and elements that you maybe know something from databases, maybe if you have to read some lectures about this, there's similar problems with lost updates and so on. If you're not to do a proper, let's say, protection of these regions, and we talk about this in the second part of the course. And before we close then with the second part, it's important to understand really where the differences are between MPI, what are the performance issues, what are the limits of shared memory, why we need hybrid programming essentially. And of course, there will be some application examples along the line. So with this, we fulfill some promises, of course, from earlier lectures where we said, okay, shared memory is not what we focus on. We focus on distributed computing in the beginning to also work now on your first assignment before we now come basically to this assignment with shared memory. With this, you basically have an idea that scalability is enabled by hybrid computing, and still the tasks and threads that you can execute are really data-intensive ideas when you want to have a loop and so on and work on data. So you are basically already having the counterpart of MPI to do really complex aspects of parallel programming, not even maybe going to hybrid programming at the beginning, but this would be certainly something where shared memory at some point will be having limits. And it's very obvious that you then have to go to MPI. And we will show you some examples with HPDB scan, for instance, how you can combine this. And of course, not the complete source code. We would otherwise need a complete hour just on the source code. However, with this lecture today, you have again a very complex aspect of parallel programming understood and can really start and use HPC programming applications in practice. So let's go with shared memory programming concepts. And there are basically two varieties of these shared memory systems. You know that already from our first lecture. There's this unified memory access and the CC-NUMA, the cache coherent non-uniform memory access. Basically, these for the developer are still, let's say, very similar, right? It's a cache coherent idea will protect the developer of thinking that this is inherently a distributed system. So it is a shared memory system because we have this cache coherent link. We learned this the last time, right? And of course, still the cache coherent protocols, still as developer, and you see that a little bit here, gives us still the idea with the bus interconnect that it is all one shared address space, although it's in fact distributed. Hence, we as developers don't necessarily need to know this, or basically will not program against it and can port applications to it because the underlying cache coherent protocols will help. In generally, and this is now an important part, when you see here T1, T2, T3, I was alluding to this in earlier lectures as well, that we are not talking about processes here anymore, but more rather lightweight processes that we are calling threads. And each of these threads, of course, as the name suggests, is address having access to the shared memory address space that you see on the right hand to read and write variables, do something with them, of course. And this is now really the idea of shared memory, and OpenMP is now the dominant shared memory standard that we're going to use today, which essentially is now interesting to understand that it's much more, let's say, changing source code with so-called compiler directives, marking parallel regions. So we're not talking about essentially doing this message exchanges with MPI. If you remember, that's why I modeled it a bit differently, right? Where we said from A to B, we did a broadcast, whatever. Here we're talking about compiler directives. So the communication essentially is again not really there, but rather, through the shared memory address space, of course. So let's look at this a little bit, UMA and CC NUMA quickly again. Although by now you know the fact that these are almost similar from the programming, but of course from the architectural design on the chips and so on a bit different. For us, however, it's important to understand that the memory model that you have, including caches, is of course very beautiful. So when I say you have to use distributed memory, that's not, of course, not really necessarily for speed, because having so many level of caches, and this is by fast, that is the fastest that you can have to have storage, getting back into the, let's say, chipset itself to do really work. So hence memory is expensive, right? So, and this is the fastest option, but as you also know, it has a certain amount. So basically this can also not be changed of putting more and more memory to all the cores. So hence, in other words, we really need, let's say, extension of this. And a little bit, you see that here with the extension of CC NUMA systems, where the network logic we said already has this cache coherent link where we have different, let's say, distributed memory systems, but they are designed with this cache coherent link, again, like a CC NUMA system, which means it is for us as programmers not really visible that there's, let's say, different memory spaces. And again, we benefit, of course, from the different layers of caches here and so on for each of the different processes. So in this ideal world, you would say why we don't have just large CC NUMA systems, but also this is not really possible at scale. Hence, we have at some point in time the limit that you see here enforced by this memory and this memory of the, let's say, physical space in the memory that even is maybe an aggregated single address space for speed, but still is limited in terms of scale. So meaning also we have to talk a bit about the shared address space, but I think many of you that had the basic lectures in computer science at least should know a little bit about this, that of course you have here two examples. You have two threads here, which have their own data, right? And their own stack with all the data. But when they now write into the memory, right? So this is during the execution, they have their own private data per thread and the same variables maybe. But when they want to write something to memory, they have the shared address space. And this shows you that, one thread might write into the shared address 23, then another thread can actually use it and uses here with a simple addition of +1 and can actually work with it. So read and write is simple. We don't need message exchanges. We just have the variables. However, you notice also it depends now if really thread 1 was finished in order for thread 2 maybe to start. So you see, in other words, these two green and red lines show you already some of the trouble that could come, that how to understand that the memory variable was written at the correct time, is read at the correct time and not at the same time, and so on and so on. So, and this is where OpenMP helps, for instance, but also for other things. I give you also a kind of visual interpretation, because I know that we have also several bachelors maybe from other fields in computer science, so that maybe are not so familiar with this. Again, the point is that the processors can still, without really message exchanges, write into the memory and read into the memory, read out of the memory. And this is true for NUMA, but also CC NUMA. UMA and CC NUMA, which you see here. So in other words, you don't really have to program any message exchanges that we had in MPI. We access a local memory. I think I have repeated this enough. So let's come to the OpenMP as a library for being one of the de facto standards really in high performance computing for shared memory. And basically we mark parallel regions in a code which is essentially serial, right? So, and this enables us still lots of scalability. We can have speed ups actually. And also we, of course, need to have, let's say, specific workloads and so on that matter to the problem and the suitable data, let's say, idea, how we then can do this parallel processing. For instance, a loop, which we'll come later to. And it's important when we talk about OpenMP that you think about much more threads, right? Lightweight threads that are basically lightweight processes, right? Having then the share of the common address space, but their own variable stack and so on. And they're a little bit less heavier than a complete process, right? So this is an important part. When you think about this coding, think about threads and not processors. And the way how it works is now influenced by several important terminologies from the OpenMP standard. So first, you would say you have this master thread, and this shows you also quite nicely the picture that we had with the array, where I was, having the maximum of the array. You could depict it here. You would say, okay, the master thread is working. Then we want to have a parallel region where we do the maximum of the array. Here we have 5, not 4 threads working on it. And then, you join. And in the serial region, you would maybe do the max global, right? And still the master thread has to work here. And the master thread becomes the first thread also in the parallel region, right? And then you do something else with a team of threads, which not necessarily needs to be 5, could be 4, etc. And this is sort of the OpenMP program idea in parallelization. So you see that there are some elements in the source code where it actually makes sense to do it parallel, but others keep it serial. And you see that a little bit here in the same analogy. You have a sequential part, a parallel part. This is a parallel region, and then we go back to sequential, and then again a parallel region, etc. How you do this is so-called, with the sentinel. You see here this pragma or MP parallel. This was what we call a sentinel, and stands usually in front of a parallel region that can be many different things. Could be something, we know as loop, for instance, as the simplest, perhaps. And you see here different examples basically in Fortran and in C. So, of course, we still need C. So OpenMP is essentially just influencing then with compiler directives the C execution, right? And this is something which you really have to understand here, right? So we're influencing a C code which is inherently serial, and just by adding some compiler directives, I make it parallel. Still, the C code needs to be programmed in a way that this is actually possible, and we will make some, let's say, points on it. Important is also to understand not only the serial regions versus parallel regions, but also that the master thread has a life that goes through, let's say, the whole MPI program. So it's a backbone, right, of the OpenMP program, where you have the master thread here, parallel regions in 3 threads something. You see that nicely depicted here. It always survives, so to speak. Even if you collapse a parallel region, we are back to the master thread to keep the whole work and to keep the whole, let's say, idea of the parallel program working. Again, here's a good example. When you come to this, you see there's a function you call in the serial region, which is just executed by the master thread, and then you have pragma MP parallel, where you then execute Billy a couple of times depending on the number of threads, and we will come to that, how you steer the number of threads, dynamically perhaps. And this will then also collapse at some point in time and done the work, and then we do a serial work here with Daisy, whatever. So these are just examples. The benefit we have, of course, is then thinking about a standard that also enables us to see the bigger picture of HPC machines. Right now, again, the portability is something we are very interested in, because in EuroHPC, in one of the earlier lectures you learned, we have many different systems in the union. So chances are that you get computational time on one and continue with another, computational time and on some other machine, and you want to have your OpenMP program working. And of course, you remember that also from the MPI lecture, right? So this was sort of the similar idea with MPI. Let's have a standard so that every time we use another HPC machine, we can, let's say, port an application, not only MPI, but OpenMP, and also the hybrid ones with this. Of course, And this has limits. I mean, first of all, given the quantum momentum now, this is not working directly with quantum computing systems, right? Here we talk about different HPC systems. However, you also have to think about different vendors have different technologies. The amount of memory that you have per node is maybe completely different, right? It's an older HPC system versus a new one. The clock frequency of the CPUs, in other words, the speed, might be very different. So in this sense, also the whole OpenMP application works different with the threads. So this is all, of course, enabling you a basic portability and works quite nice if you adhere to the standard OpenMP. But still, of course, there are limits in the other end when you look, on all the different heterogeneity of the systems. Still, it's good to take this basically into account and use shared memory. Especially then also, of course, when you think now about the bigger picture, we said basically the large HPC systems are programmed in a way that they're, let's say, more hierarchical hybrid computers. What has this to do is essentially that you see here nodes where you maybe have, let's say, a shared memory system here. They all can happily access the shared memory system. But when you want to have a bigger and bolder your simulation that doesn't fit into the memory, or you want to have more speed up, you always have to add some other nodes. But with this, you can't access the memory anymore. You have to use a network interface, the communication network that you do, and you do this usually by using MPI messages. Hence, this enables us now to think a bit more about hybrid systems. So just have some motivation, and I would give you also here a link to some tutorials for those of you who are really, and I learned some of you during the industry projects in our course, so that's really good to know that some people are really interested in MPI programming and doing much more. And you have here in Praise tutorials quite a hard amount of materials, right? Videos, tutorials, which go far beyond the material produced in these lectures, because we have our HPC not only focusing on MPI and OpenMP. So also here, you see with the OpenMP videos here, it's something that you really can, let's say, have a good insight on how to do OpenMP, and then also combining this with MPI videos here, you will learn how to do more hybrid system programming, where you combine then the power of distributed memory and shared memory techniques, right? So, and this is the point where I said, also on the other side, maybe, MPI instead of, OpenMP would make no sense, right? You would copy what you see here as an example, because of course, essentially you could say one processor talks to another. You can do this, right? You could do within a node MPI, but it usually is not really very useful because you will copy the buffer, if you remember, in the memory, what you want to send. But you also, of course, have a copy of the buffer, what you want to receive before you write it to the variable. So in all, it's quite a big overhead because you have the access to the shared address space, right? So this is sort of a memory copy with MPI, and to do this is, so to speak, not really useful. Hence, by programming them, you would do different things and would rather see essentially that you program within a node with shared memory, right? And this is always possible. You have your paradigms. And of course, in the second part today, we will also learn a bit about the programming of it. So sentinels and how we steer this with variables, the parallel regions and sentinels. But of course, we know then, of course, this is limits. And for instance, the memory is not enough for your application. Then you think about distributed memory across the nodes. Hence, the hybrid programming stands a little bit for it, that, you have always, this kind of idea, shared memory within the node to really leverage the speed of the caches of the memory. It's fast, but limited in terms of size. So every time you go across the node, you do now MPI messages. And this is, of course, an opportunity to scale up quite heavily, right? As we see with some of the applications. So you see that also a little bit here depicted. Again, OpenMP within the node, right? Each for itself, of course, can use OpenMP. So you need to have your application in a way done that some things can be speed up in the different region, let's say from your domain decomposition, and then, basically compute the wave height, for instance, that we saw over the ocean using OpenMP in parallel within the node to leverage maybe the whole, let's say, idea of the caches and the memory access. But then when you see about the bigger time step of the whole ocean, you have to communicate with your neighbors. So what was my wave height here with shared memory in order to communicate to the others, my wave height with MPI. So over the network, over the node. And this is sort of the hybrid system programming idea where you now combine MPI with OpenMP, which is very often done in applications today, right? To really have domain decompositions that are scalable and that are also, let's say, giving you the opportunity to go way beyond the typical memory you have. And one example I want to show you is out of our own research. I already gave you this example as the MPI example because it's also an MPI code, right? And you have here this DB scan algorithm. We call this HPDB scan because it's for high performance computing, implemented from Markus Götz, one of my PhD students in the past who finished his PhD already. And you see quite nicely here in the scaling plots that we did at the time that the MPI with some data set 1, which is essentially different data sets here of the city to really cluster back from a point cloud measurement, just basically points in space. We cluster back the city parts, so basically the buildings based on Euclidean distance again, how close are the points, and then giving different colors, etc., etc. But here is something where you clearly see with MPI, at some point in time, we break off with a performance, right? So when we add more and more cores to this data science problem, there's some trouble and overhead with it. Now, when we do with both different data sets, a smaller Bremen and a large Bremen data set, and add here the hybrid one, where we actually implemented OpenMP and MPI in parallel and using it in parallel, hence the code can be used with MPI only, or you switch on, let's say, that within one different region of the clustering, there should be also the power of shared memory used by using OpenMP statements. You essentially are in the hybrid domain with different data sets, and you see that you already actually scale better, right? While data set 2 is a bit an unfair comparison because, we have to see data set 1 here with data set 1. You see definitively the hybrid version is scaling better. Still, of course, the ideal scaling here that you see what you probably is hard to reach for every, we usually say something, it is near linear scaling, right? So it's not directly linear scaling. It will be always breaking off at some point in time, probably, especially if you now talk about exascale resources coming up in Jülich, like Jupyter. And the way how it works is a little bit, influencing also the job script that you by now know very well from my MPI, right? So, and also thinking about much more these elements and tasks per node, right? The last time we thought about nodes and tasks, but we didn't thought about too much what are now the tasks per node. And basically we kind of crunch down the problem even more in detail here, right? And CPUs per task that you see there. Oops, that was a bit too fast. And we give them also here different threads as an input, as a kind of input to the application so that the application can know how to expect, how many threads it can expect. And with this, the implementation of this whole, let's say, is done really in a high performance way that this is then much more better than just using pure MPI. Good. So before we break today, I also want to give you some, let's say, outlook how it also influenced more and more GPU design. And I think here OMS and the evolutions of OpenMP, where you think shared address space can be also a little bit the idea of a device memory now, right? So we have the host memory of the CPU and the device memory. We have learned that a little bit already in earlier lectures, and we will dive into more detail definitely in lecture 5. But you see also here how OMS over the time basically has influenced the OpenMP standard, right? OpenMP 5 and more these days. And to a way that there's more and more a view perhaps on task computing, if you will, right? So what are the tasks that are computed with this and seeing bigger pictures? And that's why I like to show you this, but this is something what we don't really want to tackle too much in the course. This is about workflows, larger view of problems, dependencies and trees of executions, where you can essentially see that when you break up one serial source code into parallel parts that are dependent on each other, you come to sort of an execution tree, right? And part of this needs to be parallel. We see here some sentinels, right? Where you have the task idea already basically shown here from OMS, where the programming model is much more task-based than just having a parallel region and you're on your own. So you can have a couple of more influence if you want. And this is sort of driving more and more the OpenMP standard. You see here also different ways how you can now do the parallelization over different domains, really, up to maybe also here functional decomposition a little bit. What are these different elements doing, and having then inserted some task dependencies on this. So this is all something which OMS stands for, and leading also to some development of PyComs, which is then trying to do similar aspects now in Python, and is basically a framework to have applications now on a bigger picture, right? So where you want to have some tasks executed, and OpenMP is very low level, it targets one shared memory, but with COMS and PyComs now you think bigger and think that it might be not only this one HPC machine there, it could be also two other HPC machines somewhere. As long as my tasks are executed, could be maybe even using some EC2 cloud parts, I'm fine. And of course, the bigger your problem, you might be needing this, right? Again, thinking about the restrictions that shared memory is not so, let's say, powerful in terms of the size of the memory. So here you have a way of making applications bigger, and that's also sort of showing you how the developments of your projects. You have seen a little bit also the Deep project again. There were some developments on this also within the project that also influenced the OpenMP standard again. So much for the OpenMP overview, right, which we had in the first part. You see here in ocean wave simulations, I was talking about this a lot. So here you see an example how this works with CFD. Reza will go in later lectures also much more into CFD. But this would be one example where you can have a small ocean part perhaps also simulated nicely in shared memory. But then if you want to have the whole scale, then you'd quickly at the hybrid programming. We stop here before we go to real programming basics after a short break.